Just to give you an introduction to myself, my name is Scott Johnson, and I worked as an extension specialist with fruit crops with the University of California for 31 years. I was stationed near Fresno, where we grow a lot of peaches. I was mostly a peach specialist, although I worked a little with apples and pomegranates and kiwis as well. So as an extension specialist, I worked an awful lot with just very practical field type experiments and programs. So I did a lot with thinning, chemical and mechanical thinning, and I dealt with rootstocks and planting systems, a lot with nutrition. And I would say my passion, though, was water. That's one thing I worked a lot with, irrigation and figuring out how you might reduce water input into an orchard. Very important in California, but I think it's going to become increasingly important even in Utah here. We're not quite in the drought situation that you read about in California, but a lot of people like to live in Utah, and as more and more people come, there's going to be kind of less and less water, and it's going to be a challenge for agriculture to get the water they need. So I think all the things I worked on in California pretty much pertain to what you see here in Utah. So hopefully I have some useful information for you today as we talk about irrigation. I do encourage you to ask questions. I know I can't cover everything that's if something isn't quite clear. Please ask questions if you want me to cover something a little more. So we'll take those as we go along. Let me just, actually your handout doesn't have this slide. It was here to remind me. I wanted to do a quick survey of those of you that are here to get an idea of what you're dealing with irrigation systems. So just by the raise of the hands, tell me in your operation, how many of you are dealing with a flood or furrow irrigation type system? Okay, so only 3, is that all? The rest of you weren't afraid to raise your hands, right? I know it's an old system. Okay, so just 3 of you. I want to just write this down. Okay, so how many of you are dealing, I'm going to separate out drip irrigation from little micro sprinklers. So how many of you are dealing with drip systems? No drip, a couple here. 2, 3, a little, just a few of you. Interesting, okay. And so how many of you have micro sprinklers of some kind? Okay, that looks like most of you here, right? Cool. Actually, that's the system that fits better into what I'm going to be talking about anyway. So those of you online who can't see the audience, most people here have micro sprinklers. Very few have drip or flood systems. Yeah, I guess I do have a 4th category. So the larger sprinkler or that sort of thing, some of you are still dealing with that. But not necessarily, it's standard. I mean, there are a couple of orchards here that actually have this center pivot overhead sprinkler system. So I guess some of you are dealing with that as well. Okay. All right, good. That gives me a little bit of an idea that might affect what I talk about a little bit later. All right, so I do want to cover a few kind of basics there, get you back to some basic physiology, anatomy that applies to water in the tree. I want to spend a lot of time on this because I figure all of you are more interested in the real practical things about how much water do I put on and how can I tell some trees are stressed and those sorts of things. So, we'll try to get that to that as quickly as possible, but I think you need some background in terms of...
Scott, can I stop you for just a second?
Sure.
If anybody that is online has your mic live, please mute it. I'm monitoring and I can hear somebody rubbing back and forth on their desk or something accidentally. So if you're online, mute your audio, please. Okay, thank you.
Okay, good. So a few basics here about water relations in the tree. Some anatomy first. I'm sure you all remember this from your biology days in school. You have in the trunk of a tree, you have right under the bark what's called the cambium, which is the meristematic tissue that's producing xylem to the inside and phloem to the outside. Xylem is the conducting tissue for water in the trees. And basically, they're just hollow tubes that are dead cells that are conducting water up the tree. And the phloem on the outside of that cambium layer is transporting the sugars up and down in the trunk. So the xylem is what we're particularly interested in when we're talking about water flow. And once water gets up into the leaf, a leaf has a very high concentration of water, and so even the air in the leaf are basically at 100% relative humidity, saturated with water vapor. And that water then escapes to the outside through these little openings that we call stomates, stomata or stomates. And the plant can control the opening and closing of those stomates. So water is lost quite rapidly out of those stomates, but they're the same opening through which carbon dioxide enters the leaf for the process of photosynthesis. So that's, many plant physiologists have called the loss of water from leaves or transpiration a necessary evil that plants have to do because they've got to open those stomates to take in carbon dioxide for photosynthesis so they can grow. So if any of you want to become rich and famous, if you could invent a membrane that would allow penetration of CO2, not H2O, you would become very rich and famous. So, because we could grow plants with a lot less water and still allow them to photosynthesize. So far, nobody has come up with that because H2O is a smaller molecule than CO2, and so most membranes and don't allow, they let both go through, or if you make it small enough holes, it'll prevent CO2 from going through, but not the water. So kind of opposite. All right. So those are the stomates, and the plant can open and close the stomates. Typically, the stomates close at night, although not in all plants. Or when they get very stressed, the stomates close. For the most part, the fruit trees that we're talking about, cherries, pears, apples, peaches, pretty much open their stomates fully during the day as long as they're well irrigated. In some plants, you might see a midday closure, but not typically in most of our fruit trees. So they're just kind of losing water like crazy during a typical day. Typical hot day that you see here in Utah. Okay, so one other important aspect of the water that allows water to climb up through trees, what's called hydrogen bonding. Water molecules are basically little magnets. They've got a positive side and a negative side, so they attract each other and kind of grab onto each other, so that allows water to be pulled through the tree. If you see a water droplet on a waxy leaf like this, the reason it beads up like that is because of hydrogen bonding. Those little water molecules are holding on to each other and preventing that drop from spreading out. Okay, so that's a very important aspect of a very important characteristic of water. All right. So, as you know, water flows from out in the open, from a place higher up to a place lower down, basically controlled by gravity. Scientifically, we say it's moving from a position of high water potential to lower water potential. When you get into a tree, it's the same principle. Water is, but it's moving up the tree. It's moving against gravity. So clearly gravity is not the force that's moving the water. In fact, the force driving water through the tree is provided right at the leaf surface. So through the stomates, as you have water, saturated water vapor inside the leaf going through the stomates into air that's less than saturated. Sometimes in Utah it's only 10% relative humidity. So you have a very strong driving force that's pulling that water out of the leaves into the atmosphere. And then all the water molecules behind that just kind of pull each other up through the tree. So you have this constant suction of water being pulled through the tree. It's not being pushed at all, it's being pulled through the tree, and the driving force for that is the transpiration, the evaporation of water from the leaf surface. So the way we measure that is it's called water potential. You see over on the left hand of the screen there, the water potential measurements that you find throughout the tree, and we'll talk about how you measure this in just a minute. You can certainly see that they're right as the leaves going from the air spaces to the outside air, minus 70 to minus 1,000. It's a huge difference. That's the driving force that's pulling that water out of the tree. Okay, so by definition, water in an open container, in a lake or in a bucket, at sea level, at room temperature, is given a water potential value of 0. Okay, that's just by definition. So anytime that water moves through the tree, it's going to be lower, in other words, more negative and more negative as you move up through the tree. So this gradient that we're talking about in a tree is always a negative value. It's moving from a level of less negative to more negative as it gets pulled up through the tree. Okay, so the unit we use is called bars, typically. You're probably not real familiar with bars, but just relate it to what you are familiar with. 1 bar is equal to 15 psi. So, you know, when we're talking about a leaf that's at minus 10 bars, that's equivalent to about 150 psi, which is a pretty strong force. We fill up our tires to what, 35 psi, and if a tire bursts, I mean, there's a lot of force there. So when you're talking about 150 psi, that's 10 bars. That's a strong force that's pulling water up through the trees. And when the tree gets very stressed, I've measured water potentials as low as minus 40 bars. You know, that's about 600 psi with a very stressed tree. And it just kind of gives you a sense of the sort of strength of power that's needed to pull that water up through a tree, especially when it gets very stressed. Okay. And just one terminology here, when once a tree gets really stressed and that column of water with all those little molecules trying to hang on to each other, once that gets to a certain point, that'll break. And you have what we call cavitation. You can actually hear a little snap when a xylem column breaks, the water column in there breaks. And of course, once that happens, the tree's, or at least that xylem vessel, it's kind of out of luck. There's no way to keep pulling water through that vessel. So you get a lot of that going on and a lot of cavitation, and the tree pretty much dies. So we're going to talk a little, as we talk about instruments, we'll talk more about measuring water potential. This is a pressure bomb or a pressure chamber. The principle behind it is pretty simple. You just have a pressurized tank there underneath, and it goes into this little chamber. You put a leaf in that chamber with its petiole exposed, and you apply pressure until you push water back out of that leaf. And that tells you how much tension, how much that leaf had to be pulling on water to get it up to, from the soil into the leaf. So that's a very useful instrument that we'll talk about a little bit more later. Okay, and then let's just talk a little bit about water in the soil. This is what we call a water retention curve for soil. And this is just a plot with the water potential on the x-axis here versus water content, either the volume or the mass. Those are just two different ways of expressing the amount of water in the soil. So you can see very big differences from a sand to a loam to a clay soil in terms of how those relate to each other. So as you know, a very sandy soil, a pure beach sand, doesn't hold a lot of water. In this particular example, they're showing that at this point, well, let me define a couple of terms first. Field capacity is basically the amount of water that your soil holds right after the irrigation. Once you've maybe left a few hours for the water to drain out, that's not being held by the soil. So, and generally that's been given a value just of minus 1/10 of a bar. It's almost like you've got the plant sitting in a bucket of water. So it would, a bucket of water is 0 water potential. So this is just slightly more negative, just shortly after an irrigation. So this is filled capacity. And then we've defined the wilding point, or sometimes it's called the permanent wilding point, is the point where that plant has an awfully hard time pulling that remaining water out of the soil. And it's given a value of minus 15 bars, which is pretty stressed. Most plants are pretty well dead by the time you get to 15 bars in the soil. That's a lot of work for that plant to try and extract soil at that point. So the difference between this and that has been called available water, which I think is a little bit of a misnomer. I mean, out here it's very available, and as you get close to the wilding point, it's barely available. So you do have this area in here where you have some water that the plant can use. And as you can see, for a sand, not an awful lot. Their example here just shows you about maybe 7% of that total volume water that could be used by the plant. Whereas for the clay, you're up here at 50%, and you can use an awful lot of that water before it starts to get seriously stressed. So big difference in these soils. A couple of things I just want to point out here. There are different instruments for measuring water in the soil. And if you have an instrument that just tells you the percent water, that doesn't tell you at all how hard it is for that plant to get that water. So for example, if you've got 20% water in a sand, at this point, a lot of that water is going to drain off, but it's of course very available. Whereas in the clay, if you've got 20% moisture, that's water it's not even available at that point. So the percent water, if you use that measure, you kind of have to know what soil you're working with to know how available the water is to the plant. Okay, so typically, let's see, this next slide shows you kind of the typical amount of water that's available in different types of soil. So for a good orchard soil, a sandy loam, you have maybe 1.5 inches of water per foot of soil. So that's telling you that if you have 2 feet of rooting depth, you've got maybe 2.8 inches of available water that can be used, by that plant. Typically, this varies, of course, from situation to situation, but for the most part, we usually figure that you want to be, especially if you're flood irrigating, you only want to go to maybe about 50% of your available water being used up before you replenish the reservoir in your soil. So for our example here, with the sandy loam, if you've got 2.8 inches available water, you want to be irrigating after you've used about 1.5 inches, which in Utah is about once a week, typically. Often the evaporation is about 1.5 to 2 inches per week. Okay, and you can see, of course, that it's very different for a sand soil or a clay soil. All right, so that's kind of it for soils, I think, and yeah, I think that's all I wanted to say about basics. So go ahead, questions here. Okay. I mean, it tends to. I mean, a gravel holds water even less than sand does. So I mean, it's going to be even worse than sand typically. I mean, it depends on what else is in the gravel. If you've got some clay and so on, then you'll have a. Yeah, they do. So it's a challenge. I mean, it's the way they develop these curves. So if you want to do it as scientifically as possible, you take a sample of that soil and wet it up so that it's at filled capacity, and they put it in a little pressure chamber and then just apply different amounts of pressure. Essentially, they're just moving across the x-axis here and then measure how much water is left at each of those. So, if you've got access to, there's places like Utah State that might do that for you, some of their soil scientists. So technically, that's probably the best way to do it. I think we'll talk a little about tensiometers. I don't know if you've ever used a tensiometer before. Tensiometers measure the water potential of a soil. So you can kind of put one of those in and at least get some experience with how that changes as you irrigate and as it dries out, and you see what's happening to your trees. So it is challenging though. I mean, because sometimes you're talking about boulders and things like that, and all of those can have a major effect on how well that soil holds water.
I was wondering if they're moving towards plant sensors,
Right.
to measure the tree stress. Is that
We're going to talk about that. That's actually, in my opinion, is the best way to go. Is ask the tree how it's feeling rather than trying to figure. I mean, the soil is so variable and there's all sorts of problems. So yeah, we'll talk about that here as we go along. If I don't cover it well enough, then ask more questions. So, any other questions then about some of these basics? Okay, cool. Well, let's move on then. And talk about water use in trees at this point. Ultimately, we're trying to get to the question of how much water is my orchard using? How much water are my trees using? So I know how much to irrigate. So we've developed a fairly simple formula here that is pretty widely used now that can, for any crop actually, can tell us how much water these trees or whatever plant is using. So the tree water use, which we call ET is for evapotranspiration. So it includes both the evaporation of water from the soil, and transpiration is the evaporation of water from the leaves through the stomach. So the ET of your crop is equal to a potential ET, which we call ETO, times some sort of a crop factor. So ETO is just kind of the potential of what you can, kind of the most that you might possibly use, that trees may use. And then the crop factor, this KC, which we call the crop coefficient, can modify that depending on what's going on with your individual crop. Okay, so let's talk about each of these. We'll talk about ETO first. So as you know intuitively, when it's hotter and sunnier and drier and windier, your plants use more water. You know, so when it's cooler and cloudy and the wind's not blowing and the humidity's higher, then you use less water. So scientists have basically developed a reference crop that's pretty universally used now, that is defined as just a grass field, a mown grass field, and they've developed equations that predict how much water this field of grass will use. So you can just put out a weather station that measures all these different weather parameters, and you come up with, you plug them into this formula. I don't expect you to remember this formula, but basically you have a formula that is dependent on these different environmental factors to tell you what your potential water use is for that particular situation on that particular day. And it's dependent, and this is in order of how important they are. First on solar radiation, second on humidity, third on temperature, and fourth on wind speed. By far, solar radiation is the main driver there. So that, for example, if you got a nice sunny day and it's 90 degrees out, your ET won't be that much higher if it's a real sunny day, but it's 110 degrees out. The temperature isn't nearly as important as the solar radiation. On the other hand, if it's 90 degrees and sunny versus 90 degrees and cloudy, you can have a 2- to 3-fold difference in your potential evapotranspiration. So, you know, once you plug them into this formula, you generate these daily ETO values, which we did in California. They also do here in Utah. I'll show you an example from California, where I worked. I was at near Fresno. If any of you have been there before, it's sunny and hot and cloudless every day of the summer, just about. And so you actually get there are advantages to that. It's maybe not the greatest environment to be in, but it's very predictable and very uniform. I mean, the only cloudy days are where you see these little dips here. So the maximum that you reach follows this curve that is pretty much a function of the length of the day, how long the sun is shining that day. You know, reaching a maximum here on the longest day of June 21st and dropping off on either side. So, and this is from year to year, it's very similar and very predictable. I plotted it out for Spanish Fork here, this area right here, and you get quite a different picture. Notice a couple of things that are different about it. First of all, of course, highly variable, especially in the spring, as storms are coming through, and it can be cloudy one day and not the next. And you can see, I mean, the difference can be 3, 4, 5-fold from one day to the next in your potential evapotranspiration. I also found this rather interesting. You'll notice that the largest values that we get in sunny, hot California, when it's 105 degrees every day, the highest we get is less than 8 millimeters, which is, you know, a little less than 1/3 of an inch per day. However, here in Utah, you have some days that get up to 9, well over 8 millimeters. And I went and looked at those days. Those often are, you know, these hot sunny days, but the wind picks up on some of those days, and you get these 20-mile-an-hour winds. And it can be really dry. You get down to 8 or 10% relative humidity. So you can, not only do you get this variability with the weather, but I mean, it's much more extreme than what we get in California. So to me, the take-home message here is, in California, we can kind of depend on historical averages and use that for ETO. In fact, we've developed these maps that kind of show you from year to year, you know, depending on your location. On June 10th, that's how much your ETO is going to be, pretty much from year to year on the average. Yes, question here.
That graph on Spanish Fork.
Right.
I know that you've got a Hemi here, you get Hemi. Is that the only location in Utah where you've taken those figures? Have you taken them out like at West Mountain or Genoa or any of these other places where the wind factor might be different?
Right. So I apologize to the online people. I forgot to repeat the question that was asked before. So the question here now is this graph that we showed you of Spanish Fork. The question was, has this been done for other locations within Utah? And the answer is yes, absolutely. There's quite a series of weather stations throughout Utah where this information is collected. And you can go on the internet, I'll show you where in a minute, and go to the location you decide is best for you and find out exactly what you know, your ETO is there. So yeah, I mean, it depends very much on local conditions. So with that weather station is right where there's a lot of wind coming through, it might be even different than 2 miles away where it's more calm, which makes it a little more challenging. In some cases, you might want to put up your own weather station. Decide for that location that this is the best average weather for here. Okay, does that answer your question? All right. Okay, so just to kind of finish my point here, I think it is important within Utah that you don't just use historical averages. You kind of have to keep track of the current weather conditions, because it can make quite a difference on how much water you're using during certain periods of the year. So, all right. So once you've established your potential ETO, your reference crop evapotranspiration, then the next step is to apply this crop coefficient for your particular crop. And again, with fruit trees, I think there's mainly just one factor we need to worry about. If you start talking about, I mean, there's plants out there that even when well watered, try to conserve water by closing their stomates. Not true for our fruit trees. And of course, there's desert plants that have whitish leaves, so they reflect more light, or they actually can turn their leaves so they're parallel to the sun instead of perpendicular, and things like that. Again, our fruit trees don't seem to care about saving water, so they you know, their stomates open up, they just transpire away when it's as long as they're well irrigated. But what is different and what kind of determines the crop coefficients is the leaf area development. Clearly, when you don't have nearly as many leaves, they're not going to use, you know, a lot of that sunlight doesn't even hit the tree. It falls on the soil. And so you're going to use less water. So people have developed these graphs of crop coefficients for different, these are all different deciduous orchards in California. And I don't show you which is which, but the difference with all of these among them is, first of all, kind of when they first leaf out. So in different locations, or some crops, as you know, some trees don't leaf out until a month after others. So kind of when they first leaf out is when you start, you want to start irrigating. And so if you were to graph all of these based on leaf out day, you'd find they're all pretty parallel, pretty much the same. So you start with that date, and then you see that they pretty much level out by the beginning of June or so, pretty much the same sort of time. And then they drop off at the end. We'll talk about that in a minute. So it's fairly simple. You just start with a crop coefficient. In this case, they're all about 50% of potential ETO, and get up close to 1.0 or 100% of ETO by summertime, and kind of maintain that level for the rest of the summer. So that kind of that makes it pretty simple to figure out what your crop coefficient is. However, I'm going to add one more thing that we figured out in California. We had the advantage of having what's called a lysimeter. Lysimeter is just a big box in the ground like this. And in the bottom of that box is a very sensitive truck scale. And then on top of that scale, within the box, we have this planter box. It sits on the scale and it doesn't touch the walls on any side. So we can get the weight of that whole system, put all the soil back in it, and plant a couple of peach trees in there. So we can get the weight of that system continually. And we actually had this going for 20 years. So we have a lot of information basically about water use, hourly water use, and then of course daily and seasonal water use of these peach trees. First when they're small, and then as they got bigger, and we eventually had some very healthy, mature peach trees, 2 different varieties that we planted at different time, looking at their water use. So the crop coefficient that we developed for peaches looked like this. So the almond one is very similar to what I just showed you, and would be typical of a cherry or probably even an apple. This sort of a curve, as I showed you, it starts at about 50%, gets up close to 1, and then drops off later. The difference between all those crops and the peach is basically how you prune them and how the leaf area develops. Most of our fruit trees have spurs. We don't prune them terribly hard. So in the spring, as they pop out, you pretty much have a good sized canopy right from the beginning. And they're going to start using water pretty, not quite like they do in the middle of the summer, but they start a lot higher than the peach, which we prune very hard. Typically. So we prune it hard. So as it first pops out, there's not as much leaf area, but then you get a lot of extension growth that continues into the summertime. And so that leaf area just keeps growing and growing. And in the end, it tends to be a denser canopy, and that's more light interception than, say, an almond or a cherry tree. So for you can kind of get an estimate of this for your own orchard by just kind of seeing how the leaf area develops. And then for the most part, almost any of our crops, we can just call it a crop coefficient of 1 throughout most of the summer once they've grown their canopy out. So you use those values and apply them to the equation. And so let's talk a little about then how do you decide, how does that relate to the water you put on your trees, all right? Any questions anyway so far to this point? Okay. All right, so the first step is to go, I talked about the location here in Spanish Fork. If you go to the University of Utah climate page, they've got dozens of different locations listed there. I know there's one up in Murray, and anyway, they're around at lots of different places. And so these different weather stations can give you weather conditions every 15 minutes throughout the whole year. And then below that on this web page, you have these different tables where you can get hourly, daily values of whatever parameter you want to look at: temperatures, wind speed, wind direction, humidity, and so on. This table that you see here is called the evapo table, which is the one that we particularly want to get reference ET or ETO. So these values here at the bottom of the page are the daily potential evapotranspiration for that day. This is July of 2016, okay? So you see it's, you know, it's about 1/4 of an inch, if you can read that, per day. And then the next column is what it is for the week leading up to that day. And again, you see these are between 1.5, close, some weeks you even get up to 2 inches potential water loss. Okay, so that's the first step, is to find out for what you think is the weather station most closest to where your orchard is, what the potential is for that week or that day, whatever your time period you're working with. Okay, so that's the first step. And then there's some mathematical calculations that aren't that complicated to convert your emitter that's in gallons per hour to inches per, you know, whatever, per week. If any of you need help with that, I'm glad to help you. But there are websites where you can get that done for you. One that I think is useful is the one developed by Fresno State. It's called Water Right. That's the website there. Sit down with that for a little while and just enter some information from your orchard, and it can tell you with a given level of potential evapotranspiration and some crop coefficient that you put in there, how much you should be irrigating in your orchard. In fact, here's one other website that I've found particularly useful because it's just very simple. This was developed by the avocado industry in California. And there's only about 5 or 6 values that you have to put in here. Your reference ET that you get from the Utah State climate page, your crop coefficient that you kind of figure out. I mean, there's some that are in there, but you can just put in the program, you can kind of put in your own. You decide it's, you know, in July, the crop coefficient is 1.0. We won't talk much about this distribution uniformity, but you kind of get a feel for it by, you know, working with your orchard. Basically, if every emitter in your field is putting out exactly the same amount of water, you're at 100% uniformity. If this one over here is 3 times that one over there, then you've got pretty poor uniformity. And for the most part, if you keep your system up and running and it was engineered right, I usually figure it's 80 or 90%, you know, efficient, fairly uniform. So you can kind of make an estimate of what that is. And this leaching requirement is optional. So you just put in your tree spacing, how many emitters per tree, your output in gallons per hour, and you put those numbers in, and poof, it tells you how you should be watering your orchard 3 hours a day or whatever it is. So I think that's my recommendation, is you follow a procedure like this so that you get a ballpark figure of about how much water you need to be putting on this particular orchard. But I don't think you end there. I think you still need to kind of do a little bit of testing to make sure that that it's accurate. And that's, we'll start talking about some instrumentation here in just a minute about doing that. First of all, just I'd also recommend that you test the discharge rate of your emitters, drippers, or fan jets. It's fairly simple to do. You can trust the manufacturer. He's told you these were 8 gallons an hour, but I would still probably go out and test, plus do several different emitters throughout the orchard so you get a feel for the uniformity that you have there as well. And here's a real simple little formula. I mean, when we do it scientifically, we use these, graduated cylinders and all that. But all you need is a 1/4 cup measuring cup you can get from your kitchen, and you can get a pretty good estimate of what your discharge rate is. You collect water from that emitter just in a bucket or a pitcher for just under a minute, 56 seconds, if you remember that. But if you do it for a minute, you're close enough. And then you see how many times you fill up that 1/4 cup measuring cup, and that's your gallons per hour. So easy to do, but it's useful to do that so you get a feel for, make sure you know how much water your emitters are putting out. Okay, so let's go ahead and talk a little about instrumentation here. Any questions yet at this point? I guess, Ton, you'll tell me if anything comes through online too, right? Okay, cool. All right, so the question was, in case those of you online didn't hear the question, there was a question about instrumentation and how to measure the stress in your trees or in the soil. The original question was about gravelly soils and how you're going to measure that. And I guess my point is that soils tend to be very variable, and so it's challenging to really figure out exactly how much water is available in a soil. So you do your best at guessing at it, but then, in my opinion, the best thing to do is now to ask the tree how it's feeling. And so there's a couple of different ways to measure the water potential, the water stress in a tree. And the first I want to talk about is this pressure bomb that I mentioned before. This is a very useful instrument that I think is becoming more and more practical in an orchard situation. We used it a lot in research, and the more I used it, the more I was convinced it gave you a fairly uniform reading, reproducible, and a fairly simple reading that isn't terribly hard to interpret. There's others, we'll talk about some other methods that are being used that sometimes are a little more complicated or much more variable. So the pressure bomb, let me just remind you of how this works. So you take a leaf on the tree, cut it off, put it inside this chamber. You can see where its petiole is just coming, poking through. There's a little grommet that you tighten around that petiole so that you can keep the pressure inside the chamber. And then you slowly increase the pressure in that chamber until you see water bubbling out of that petiole. And that tells you then how, if you have to go up to 20 or 30 bars before you see water pushing out, that leaf was under a lot of stress. It was really pulling hard to get water out of the soil. Whereas if it only takes 5 or 10 bars, the leaf is much less stressed. I found over the years, I tried to train summer helpers how to read this instrument, and there's a little bit of a learning curve. I mean, once you get used to doing it, I think it can be very reproducible. Often a summer helper will try to increase the pressure way too fast, and then all of a sudden they've gone past the end point. It's already bubbling, and it was probably bubbling 5 bars ago. So you kind of learn how to approach that endpoint slowly. You also kind of learn that, if you tighten way too hard on the leaf, then you end up cutting the petiole, and then you got a problem because it's not attached to the leaf anymore. And it's just things like that. So once you've had some experience with this, it actually gives you a good, reliable value. So the question was, does it depend on where you pick the leaf, the bottom or the top? And yes, we'll talk about that. In fact, I think that's kind of the next point I want to make here. Actually, so a leaf that's been in the sun for a long time generally has a much lower water potential than one that's in the shade. And even depending on how long it's been in the sun, can greatly affect the reading that you get there. Typically if you've got a 300-foot redwood tree, it does make a big difference from the 300 feet up versus down lower. Within a fruit tree that's only 10, 15 feet tall, there's not a huge gradient typically from a higher leaf to a lower one. I mean, it might be a half a bar difference or something like that. But what's much more important is kind of the environment that leaf has been in. So what we've come up with is actually a way to measure what's more the stem water potential rather than the leaf water potential. And you do that by taking a leaf and covering it with a plastic bag, a black plastic bag. So you cut off any light that's getting to that leaf. So you stop it from transpiring. So that leaf then comes to equilibrium with what the water potential is in the shoot or in the scaffolding of the tree. And that tends to be fairly uniform. That's a fairly, within the middle of that tree, it's pretty uniform, even though these tree leaves over here might be transpiring like crazy and these much less so. But kind of that gradient going up the stem is pretty consistent and pretty, consistent there. So that's the technique that's been developed that works pretty well. And we don't call it leaf water potential, we call it stem water potential. And you have to put this bag on, and leave it on for at least a half an hour so that leaf then can equilibrate with the stem. And then you just cut that leaf off and still read the leaf. You could take the whole stem, but pretty soon your tree gets pretty pruned down if you're doing a lot of that. Put that in the chamber. But anyway, you do that with the leaf and you get what's called stem water potential. So this just shows you some example from an experiment here we did with water stress. To give you an idea of the sort of readings you get. So this the bottom line down here, the control in light blue is well watered, and I found this to be fairly true with, at least in California. I would tell growers that your leaf water potential, if you're really well watered, should be about equal to the month of the year. So in May, it'll be 5 bars. In June, it's 6 bars. In July, it's 7 bars, and so on. And you can see it's pretty consistent here. But in general, a well-watered tree should have a water potential under about 10 bars. And it's going to vary a little from day to day, or depending on how good you're reading that endpoint. But that's a well-watered condition. And then you notice some stress treatments we applied. A lot of these we just kind of cut off the water at certain points and then tried to re-water at other points. You can see how quickly you can change that water potential, getting up over to close to 25 bars water potential. That's essentially minus 25 bars. As a general rule, I found that if you can keep your water potential somewhere less stress than 15 to 20 bars, that you're not going to cause too much damage to your trees. It's when you start getting up to 20 and 30 bars that you have some problems. So, and that seems fairly consistent from one crop to another. I know that, well, some of our crop, walnuts tend to always have a little lower water potential or less stress. They'd be at 3 bars when the peach was at 6 bars, sort of thing. But again, our fruit trees that we deal with seem to be pretty consistent, so that you can go out and take a reading of a leaf, and if it says you're at 25 bars, you know you got a problem. If it's reading 5 or 10 bars, you know you're doing okay. So I think that sort of an instrument is very useful. Once you determine how much water you think the tree needs, it's very useful to go out and kind of spot check and tell you that, yeah, looks like I'm doing okay, or no, I better check that corner because it looks like those trees are stressed, and you can tell where you've got some problems. Okay, so there is a portable pressure bomb. I thought I'd just point this out. I find it very difficult to use. The one I showed you at the beginning costs about $5,000, which isn't terribly expensive. And this one is much cheaper. You pump it up, you put your foot on the bottom and pump it up like this, and that's how you get the pressure. It was designed by a colleague of mine in California, but it has a few design flaws. I mean, it might be useful to maybe take a few readings every once in a while. But for one, you're trying to read that endpoint. So if you're doing it while you're watching, it gives you quite a headache, I tell you. So, I mean, I found you get about a bar for 3 pumps. So you go 3 and look and then do it again. But it takes a lot longer. It's a real pain. It also, you're trying to cinch that chamber around the petiole so you don't get any leakage out. And even with the other units, sometimes you'd be cranking up the pressure and you hear this little hissing. So you tighten it up around the petiole so that you're not losing pressure. So with this instrument, the little screw to tighten the grommet is on the inside of the chamber. So if you didn't get it tight enough, you have to start all over, open it up, tighten it up again, and try. So it's a pain, but it's quite cheap. If you want to get one of these, let me know. I'd still recommend that you get the one with compressed air. It just works a lot better. A lot easier to use. And once you get used to it, it's fairly fast to use also. Okay, so other instruments, let's talk about a few of them that might be useful. There certainly are a range of soil moisture instruments, and I find that they can give you some information that's useful. So you have what I'm showing there is a tensiometer. I'm sure some of you have used these before. They've been around for a long time. The nice thing about these is that they are actually measuring water potential, not water content. They have this ceramic cup, porous cup at the bottom. You fill it with water, and then depending on how wet or dry, you're tugging harder or less hard on that column of water, and you have a meter here to read that. So it's kind of mimicking what the roots are feeling as it's trying to pull water up. So I found this useful. I mean, if you want to know what's happening in the whole root zone, you got to put 100 of these out because, the soil's a little different over here than there. And sometimes roots grow here, but they don't grow over there for whatever reason. But it's just kind of a check to see how you're irrigating. I found these to be useful. I've done it where I put a big long one that's kind of below the root zone, and then just watch that over time. If it's slowly drying out, you're under irrigating. And if it's kind of slowly getting wetter and wetter, then maybe you're over irrigating. So I think it can be useful in that way. And then there's a lot of other soil moisture sensing equipment. I know in recent years there's getting more and more. Some of them are expensive, some of them aren't so bad. I think, let's see, this is one we've used. It's got a little data logger with it that I think only costs a couple $100, but you can go out and basically that screen here gives you the reading from the previous 2 weeks. So you can kind of see what happened with the irrigation and how it's dried out. So these sorts of things I think can be useful just to kind of help you see if your soil is generally drying out or not. And so it can fine tune your irrigation scheduling. So I think those can be useful, but you have to be a little bit careful. And like I said at the first, you kind of have to know your soil type, because these often just give you a percent water content, and so you need to know what that means for your given soil. Okay. So a couple of other instruments that are trying to tell you what's going on in the plant. And I've had some experience with some of these. In fact, I came to Utah State in 2011 and we did a little project trying to stress some cherry trees. And this instrument should be helpful. This is called a pyrometer. It's basically just a humidity chamber that you clamp on the leaf. So it'll tell you how open the stomates are and gives you a reading of stomatal conductance, which is just a measure of how open the stomates are. Theoretically, you should be able to go up to a stress tree and say, oh, the stomates are closed, or go to a well-watered tree, oh, the stomates are open. I just found in practical use that it was highly variable and probably, again, depended on the history of that leaf, whether it'd been in the sun for a long time or not. And so you had to do dozens of readings to finally get what seemed to be a reasonable average for a tree. Because we had trees we knew were stressed, and you go read it, and sometimes seemed like this leaf is transpiring, but then a lot of them weren't. And so if you took enough, you get a good average that was a little different than the well-watered. But I don't think it's real practical, partly because of the variability from leaf to leaf. So another instrument that we use that I do think has a lot of potential once we maybe have to work out a few details. This is an infrared sensor that will give a reading of its field of view is, several feet wide, so it'll give you a reading of the temperature of a whole bunch of leaves on your tree, okay, remotely. So it's just sensing the infrared, which tells you the temperature then of those leaves. So in that same tree, we'll put a temperature sensor that's giving us air temperature. And the difference then between canopy temperature and air temperature is very dependent on how much those leaves are transpiring. Just like if you get your arm wet and blow on it, it cools it down. And so if these leaves are transpiring away, it will cool the leaves in the tree compared to air temperature. So on certain days, we could get some very nice relationships here, where the bottom line here in blue is the well-watered tree, and those leaves get as low as 4 or 5 degrees lower than air temperature. This is the difference between canopy temperature and air temperature. Whereas the stress tree, it hadn't been watered for a month, is actually 1 to 2 degrees warmer than air temperature. And then the couple in between are close to air temperature, or maybe a degree less than air temperature. So their stomates are a little more closed. So, I mean, those are big enough differences that could be very useful. And I did some of this work with Dr. Black, Brent Black here at Utah State, and they've got some students that continue to look at this. Bruce Bugby also, who is kind of the instrument guy, has developed these infrared thermometers, infrared sensors. One of the problems you have here is that when it's sunny and hot and early in the afternoon, you get this nice difference when the tree's kind of stressed. But in the morning, well, it's still sunny, but the trees aren't so stressed, you don't get that difference. And then when the cloud cover comes over late in the afternoon and you get some wind going, all of a sudden those relationships kind of fall apart. So I think it'd work well for us in California, where it's sunny and hot and the wind doesn't come up. But it's going to be a little more of a challenge to figure out exactly how to use that in Utah. But I do think it's got a lot of potential. So I just got to throw that out there as something to look forward to maybe in the future. And the way Brent and Bruce had a student just recently that just finished up his PhD, and he took some of these sensors out to some orchards and mounted them kind of where you're looking across the whole orchard. And still a little too much variability, but I think there's some potential once we sort out some of these things. Okay, so I think that's all I was going to say about instruments. Let's go ahead and take questions here.
Just on the stem water potential with the pressure changer, we had it measured those from 1 to 2 in the afternoon as well to get that.
Right. Yeah, I guess I didn't mention that. We typically try to do it right at the period of maximum stress. And sorry, the question was, or the comment was, one of the participants here has measured leaf water potential and felt that the best time was 1 to 2 in the afternoon. So, and that's, yeah, I neglected to say that. That's, you don't want to do it in the morning, you don't want to do it late in the afternoon, you want to do it kind of at maximum stress in the early afternoon. We have had some experience, nobody wants to do this, but a pre-dawn water potential can also give you, it gives you an idea of how much that tree is rehydrated. And it should only be, you know, two bars or something like that. So sometimes that can be useful. If it's up to 5 or 6 bars, then you know that tree hasn't rehydrated. You just have to get up at 3 in the morning, and that's a pain. So, all right, any other questions then on all of that? Okay, we'll move on here and just cover a little bit more, and then maybe we'll take a quick break. I did want to talk about stress. Yeah, just a little bit about, so the whole time I was in California, kind of the question I had in the back of my mind was, is there any way we can grow our peach trees with less than the full allotment of water? And so we did a lot of work with different stresses. And well, I'll give you my bottom line. After 30 years of doing this, my conclusion was that just about any stress you apply is bad. And it creates problems. So if at all possible, you give your trees full 100% ET and try to avoid stress. But number one, I don't think that's always going to be feasible. I think in California, they're already at the point where some orchards, they just don't have all the water they need. And I think it's going to happen in Utah. Either there's just not enough water, or else the pricing will be such that, hey, if I can save ½ acre of water, it's going to save me thousands of dollars, and that might be worth it. So I think the more we can understand about stress and how to manage it and how to measure it, and situations where it might actually be somewhat beneficial, I think it's going to help us in the long run. So let's talk just a little bit about stress. These are the sorts of things that happen now when you apply stress to a tree, when you withhold water. As we've been talking about, one of the first things is that the stomates start to close down. Even moderately stressed trees have a lower stomatal conductance, meaning their stomates are somewhat closed. And this tree that's very stressed might open a little bit early in the morning, but as soon as it starts to heat out, those stomates just pretty much close down completely. So of course your temperature of your canopy goes up. With the stomates closed, your photosynthesis shuts down. So the tree's not going to grow much. And your fruit growth is quite sensitive. You see these are water potentials, stem water potentials from just -5 down to -14 bars. So not even down to where I was talking about serious problems, -20 bars or -25 bars. But you see a pretty steady decline in the fruit size. Your fruit growth is going to be decreased. Eventually you get shoot dieback, you get gumming on the stem, you get more sunburn on your trunk. So lots of things like that can happen especially with severe stress. Eventually the trees die. So, and some insect and mite problems are worse, mites in particular. We found a pretty direct correlation here as we read the stem water potential the trees that were most stressed had serious mite situations similar to this, major webbing from spider mites. So, you know, lots of things can happen here that aren't good. We also found out that there's some fruit quality issues. In a peach, if you stress the tree in the late summer when flower bud differentiation is occurring, your crop for the next year is forming, you actually get a lot of these doubles the next year. They're formed in that bud for the next year, in the fall of the previous year. So you get these doubles, and then you get some associated problems like this deep suture that started as a double, but one of them aborted early, but it kind of prevented the suture from coming together on the other half of that fruit, the other double. So you get that, and sometimes you even get some split pits and things like that. So lots of fruit quality problems. But a couple of things to keep in mind with water stress. First of all these problems tend to occur with major stress. With mild stress, when you're just getting a little bit of stress, you can actually have what might be some beneficial effects. So if we can just learn how to manage stress and keep it from getting too severe, there's some benefits that can happen from that. So I mean, this is just an illustration of kind of as the intensity of water stress increases, some of the functions that happen. And you'll notice that stomatal closure, at least, I mean, this is kind of a generalized graph here, but stomatal closure doesn't happen first off. Instead, you get one of the first things that happens is you restrict some shoot growth. And so if you've got less carbohydrates going into the shoot growth, but you haven't closed stomates yet, you basically can have more sugars, more carbohydrates going into your fruit. And there are a number of studies that have shown that mildly stressed trees, fruits, have a little bit higher sugar content. Part of that might be just that you have less water in the fruit initially, but you also have the potential of perhaps packing a little more sugar into that fruit. And where you're, like here in Utah with the tart cherries, where it's used as a dry product, you're not so much interested in the fresh weight of the fruit, but in the dry weight of the fruit. And one of the first things that happens is you lose fresh weight because you're just losing water. So if you're selling as a fresh market product, any stress is going to reduce fruit size. But if you're a dried product, a little bit of stress can, cause less water content of the fruit, but the dry weight is still the same. So that can be an advantage, actually reduce some of your harvest costs, but still end up with the same dried weight yield in those trees. So some of that can be useful. And there's also studies that show that flowering with mild stress will increase. And you can, with a crop, they've shown in prunes, for instance, in California, you get more flowering, similar fruit set, and you don't thin them, so you actually get increased yields after a mild water stress. So there are some of those situations, again, where that can be useful. So stress should be avoided if at all possible, but I think there are times when it can be useful. And if we get into situations where you just don't have the water, you only get an allotment of half of what you need, we found that there's certain periods during the season that tend to be more harmful than others in terms of applying your stress. So with a peach tree that's times to avoid stress or during the early stage 1 of fruit growth, and then it kind of levels off a little, which is stage 2. But the initial stage and the final fruit swell are times you try to avoid stress. But if you have to withhold water, do it either after harvest or you can do a little during that stage 2. And you'll get less negative effects by doing that. Okay, so yeah, just, and it kind of varies with early season varieties. We worked a lot with early season varieties, so you got a lot of fruit that you pick early in the season, and so you got a long period after where you could apply stress, but you can get into these fruit quality issues that I mentioned before. So yeah, go ahead, question back there.
So on your last table, it kind of showed the sensitivity was less vital in a post-harvest, but how much does that carry over into the next growing season?
So
Do they have the water at the end of the season before the
right. So the question here was the slide here that I just showed suggested that post-harvest was a period that is less sensitive. So the question was, well, how much of that carries over to the next season? And the answer is, it depends a lot on the crop. As I mentioned, the peaches that we worked with, when we would stress some of those post-harvest, you end up with a lot more of these doubles, because that's right, you know, the end of August, early September is when the fruit buds are differentiating in the fruit bud. And if you stress during that time, you end up with a lot more doubles and other fruit quality problems. But they've tended to show in others, like almonds, they've done quite a bit of work there, that post-harvest stress doesn't seem to have any carryover effects. So it depends a lot on the crop. I think apples in general, you can do some post-harvest stress and don't tend to see any major problems the next year. So it can vary a lot by crop. Yes.
I always made a comment a couple years ago. He said that if you put cherries to bed dry in the wintertime, you'll have a lot of tree death.
Okay.
In the spring. And I don't know if it's because the roots are active and the top of the soil is frozen and you can't get the water down. It's
Right.
too dry in the deep layers, not
Right.
necessarily the top layers of the deeper soil profile. So I'm not sure exactly what he was referring to.
So,
They try to fill soil
right.
water.
So the comment was that an experienced grower here a few years ago said, don't put cherry trees to bed dry, because you tend to get more tree death. So yes, I would agree with that. In fact, with our post-harvest strategies, we've tended, we'll stress them up to a point, but then try not to put them to bed completely dry, because they are, yeah, they're weaker in that situation, and especially if you've got a hard winter, they're not going to handle that nearly as well. I think it's much more of an issue here in Utah than in California, because our winters were not so difficult. But you know, trees need antifreeze, right? They need to be able to withstand these temperatures that get well below freezing, and they do that by packing sugars and amino acids into the cells as antifreeze, so that those cells, if any cell freezes and ice forms, it's a goner. So you definitely want the trees to be healthy so that they can accumulate this antifreeze, these solutes in their cells, and stand very cold temperatures. So yeah, I think you can do some stressing up until maybe October, and then that's a good time to, before you start getting some frost, to try to re-water your trees so they go to bed not terribly dry. Okay, let's take just a couple minute break if that's all right. And I have just a few more things I wanted to say, and then I think the grower wanted to make some comments as well. So just a couple minute break here real quick. Okay. Do you usually get questions online or not so much?
Not a few.
Okay. I just have a couple more points I'll make, and then if you've got any questions, please bring them up, and then we'll turn it over to Dave McMillan. He can tell you what really happens out in the field. So I realize I gave you guys a pre-quiz, and many of you took the pre-quiz. And one question I haven't addressed yet, that at least many in the class put what I considered the wrong answer down, so I thought I ought to talk about it. It had to do with drip irrigation, and the question was, which of these statements is most accurately describes drip irrigation? And many of you in the class put drip irrigation saves water. And I considered that wrong because it's incomplete. You need kind of a qualifying statement together with that. And that is, drip irrigation has the potential to save water as long as you manage the system well and monitor the system regularly. It's in real life out there, people have gone out and analyzed drip irrigation systems, and even though they have the potential to save water, often they don't because people don't put in the time needed to take care of that system. You're always going to have leaks and plugs and problems with coyotes chewing up the hose or whatever. And so I think that was the point I wanted to make, because in fact what I considered the right answer was drip irrigation systems need constant monitoring. I think that was one option, and I felt that was more accurate than just saying drip irrigation automatically saves you water. To me, that's an important point. I've seen that a lot with growers in California. They know that they need to go to these micro sprinkler systems or drip systems, but they put them in and just kind of let them go and don't have somebody that's kind of watching that constantly to make sure there's not major problems, because a little problem can end up turning into a big problem. So I just kind of wanted to make that point with, I think I have a few more slides too. I was just going to show. Oh, yeah, I didn't quite get to this one. So I think this is to end off the stress discussion. In California, we put together this drought management webpage. I think has a lot of useful information. Kind of, if you don't have enough water, here's our recommendation for what you do with stone fruit, and then others have put in information for other crops as well. And then there's just general information too on managing water. So I think that's a useful website if you need to get into that. So yeah, I was just going to, my point here that I was making, it definitely takes a lot of monitoring to make sure you don't have some gopher that's creating problems and things like that with both drips and these fan jet systems. Also, just one other question that sometimes comes up. If you're converting a system, you've been flooding and you want to convert it to drip or fan jet, is there a problem with greatly reducing the soil volume that you're wetting? And this kind of illustrates this. This is just from an experiment with seedlings, but I think it applies to mature trees as well. Roots grow where water and nutrients are available, right? So if you've been flooding the whole area, you'll kind of have roots all over the place. And if all of a sudden you say, oh, okay, I want you to, I'm just going to water this small area of what was the whole root zone. Clearly, it takes some time for those roots to proliferate in that area where you're watering. So initially, you can have some major problems where you just, you're giving them enough water, but you don't have the roots developed in that area yet, and so the trees are going to be stressed. In the long run, eventually, in fact, some studies suggest that you maybe only need to irrigate a third of your root volume for the tree to to be healthy and grow well. You don't necessarily have to irrigate the whole root volume, but you do have to give time for the roots to develop in that area. So just the point there. So, and of course, I mean, there's just obvious problems. If you try to furrow irrigate without leveling your ground, you're just going to run into endless problems. And one of the biggest problems you have, of course, is if you've got, especially like if you've got a leak and you don't fix it and then you go drive your tractor over it, you just end up with major problems, soil compaction problems that can, they're hard to fix. So I think that's algae growing in that water there because it just doesn't drain. Yes, question.
What do you know about replenishing the water aquifer or table, whatever? Irrigating, supposedly flood irrigation replenishes that better than sprinklers. I mean, I just barely just this year heard a comment about that, and I wondered if you knew anything about that.
So the question has to do with replenishing the groundwater, basically, deep down, and what's the best way to do that? Is that what you're asking?
Somebody mentioned that flood irrigation was better for that versus whatever else, but I'm thinking, well, when you're up on the mountainside,
right,
you don't flood irrigate,
right,
obviously.
Right. So yeah, so the question is, what's the best irrigation system to replenish your aquifer, your groundwater aquifer? And it depends more than anything on the amount of water you can put on. So I think when you say that people have told you flood irrigation is better than sprinklers, it's often because you can just apply a lot more water and force it down, that way rather than, in fact, they often do it with ponding basins where you just have water there all the time and it's just kind of pushing water. So it's got to get a ways down to get down to the water table, down to where the groundwater is. But you can still do it with sprinklers. You just have to apply it long enough that you're forcing that water. Water only moves through the soil in a saturated situation. So if you only apply enough to supply the top 4 feet, it's just going to stop there and won't keep moving down. So you have to put enough, continuous supply of water to keep pushing that down to get it to.
Is that even a valid argument, though?
Is what a valid argument?
The fact that because we've switched from irrigation to sprinkler, we're going to the water.
Well, there is a valid argument that if we become very efficient at irrigating and we're just putting enough water on to supply the trees, we're not restoring, replenishing the groundwater. So it's when you become very inefficient and greatly overwater that you would then start forcing that water down deep. So there is an argument there that as we become more and more efficient, we're not very good at pushing water down deep to get it down into the groundwater.
So the point is, our well, the groundwater going down, you got to go deeper to get groundwater.
Yep.
In time.
Right. So the point that was made here is that our wells generally need to be deeper and deeper to keep, because we're using up the groundwater. In some states, like Arizona, for example, there is a very strict groundwater policy. Because if you keep pumping out a certain amount of water from your wells and not restoring that water, then yeah, your water is going to go deeper and deeper. So in the end, we should figure out a way that we're only using the amount of water that's, we're not lowering the water table. So with winter rains or whatever, we're replenishing that at the same rate we're taking it out. But in most places, certainly in California, we're taking it out of the ground much faster than we're putting it back in, even with these recharge basins that they have and things like that.
I noticed one study in California that winter alfalfa fields are being flooded to recharge the aquifers.
Right.
It is not hurting the alfalfa during the dormancy.
Right. So the comment was that in California, there are places now where they do some winter flooding of alfalfa fields to try and recharge the groundwater. They are trying to do more and more of that sort of thing in California because it's clear this is going to be a serious problem at some point where we just use up the groundwater. So we've got to figure out ways to recharge it. And the point was made that in the wintertime, that doesn't hurt the alfalfa. Probably you can do it in orchards. They've talked a little about that as well. When the trees are fairly dormant, you could probably do some of that as well to try and recharge, flooding an orchard, flooding other fields to try and recharge the groundwater.